The Big Crunch theory explores a future scenario where the universe's expansion reverses, resulting in its collapse. It suggests the possibility of a universe reboot, a subsequent Big Bang following the collapse. However, current evidence refutes this hypothesis, suggesting more that the acceleration of the universe's expansion is more apparent, possibly leading to a heat death scenario. The concept of the Big Crunch traces back to 1922, when Russian physicist Alexander Friedman found that the universe's destiny is tied to its density, which could induce expansion or contraction and not stability. He suggested that sufficient matter density could lead gravitational force to halt and ultimately reverse the universe's expansion, leading to a cosmic collapse likened to a black hole. This theory based the universe's fate on a battle of forces, the Big Bang's explosive force versus gravity. A gravity triumph would initiate the Big Crunch, reversing the Big Bang. Still, absent that, a heat death scenario is more plausible. Although we understand that the universe is expanding, the actual force magnitude remains a matter of discussion. During a potential Big Crunch ending, the universe would eventually become a massive fireball due to radiation intensification from stars and high-energy particles. Ultimately, the universe would be devoid of time, space, and everything. This theory relies on the hypothesis that the universe's matter density is great enough for gravity to overcome the Big Bang-induced expansion. Predictions from Floor cosmology can help determine if and when expansion would cease based on average energy density, Hubble parameter, and the cosmological constant. If the metric expansion ceases, contraction will inevitably follow, concluding the universe in a gravitational collapse. Evidence from the late 1990s and early 2000s, namely distant supernovas observations and cosmic microwave background mapping, suggests that the universe's expansion isn't slowing due to gravity, but instead accelerating, a discovery honored with the 2011 Nobel Prize in Physics. Additionally, the Big Crunch theory feeds into the Big Bounce theory, suggesting that a subsequent Big Bang occurs following the universe's destruction in a Big Crunch, possibly resulting in a cyclic universe. Albert Einstein's early work focused on constructing a static model of the universe, collaborating with astronomer Willem de Sitter to apply the theory of general relativity toward this aim. While initially successful, this model was quickly challenged by Bentley's paradox, suggesting that the universe was far from static, but indeed dynamic and constantly changing. Einstein initially attempted to reconcile this contradiction by introducing the theoretical anti-gravity force known as the cosmological constant to counteract consistent gravitational contraction. However, Edwin Hubble's groundbreaking studies from Mount Wilson Observatory brought the existence of the expanding universe to light. Hubble used measurements of galactic distances and redshifts in collaboration with Vesto Silfer and Milton Humason to establish a correlation between an object's redshift and its distance. His analysis of 46 galaxies led to the formulation of the Hubble constant, thereby proving that the universe was not static, but expanding. Einstein swiftly discarded the cosmological constant theory in light of Hubble's expansion revelation, deeming his static universe assumption as his greatest blunder. He acknowledged Hubble's role in elevating our understanding of cosmology during a visit in 1931. This marked a significant turning point as models of the universe shifted from Newtonian and Einsteinian visions of a static and contracting universe to one that is expanding. A new theory called the Big Bounce emerged, which speculates that the universe may undergo repetitive cycles of contraction, Big Crunch, and expansion, Big Bang, in infinite loop. This implies a scenario of incessant Big Bangs and Big Crunches, rather than a static or singularly explosive event. Albert Einstein entertained this idea of cyclic universes briefly in 1931, suggesting that a universe might have existed before ours, ending in a Big Crunch that triggered the Big Bang that created our world. This paints our universe as one in an eternal cycle of expansion and contraction. This updated cosmological model mitigates entropy accumulation by executing a net expansion after each cycle, though it isn't without its flaws. The basic components, known as brainas, are not yet fully understood, and there's a risk that the scale invariant spectrum could be shattered due to the Big Crunch. We do understand cosmic inflation and the basics nature of the forces, or perhaps the collision of the branes in the ekpyrotic model, required for vacuum fluctuations, but we're still lacking a theoretical candidate from the realm of particle physics. Roger Penrose, a physicist, proposed a new concept built on general relativity, the conformal cyclic cosmology. In this theory, the universe expands until all matter is degraded into light, making it similar to the Big Bang. With no discernible time or distance scale within this state, one could argue for a type of Big Crunch, which would then trigger another Big Bang, thus initiating a new cycle. Despite the intricacy of this model, it still has some skeptical voices. The main concern raised is the need for all particles to lose mass as the universe ages, for an inherently infinite universe to become infinitely small. Loop quantum cosmology is an innovative model, suggesting a quantum bridge between the expansion and contraction phases of the universe. The quantum geometry introduced in this theory creates a novel force, insignificant at low space-time curvature but drastically increasing within the Planck regime, overpowering classical gravity and resolving the singularities of general relativity. According to this theory, the Big Bang would theoretically be replaced by a big bounces with no assumptions or fine-tuning required. Through extensive use of effective dynamics in loop quantum cosmology, the theory provides a good approximation of the underpinnings of the universe's beginning and Planck scale physics. As numerical simulations have verified its reliability, it offers an insightful exploration of the universe, despite it varying from quantum dynamics in the later stages and the persistence of significant quantum fluctuations in these instances. It might overestimate the density at the bounce, but should still represent key qualitative aspects accurately. In the speculative scenario depicted by Paul Davies, the universe undergoes the cosmic Big Crunch around 100 billion years into the future. This model proposes that the universe, much like a mirror reflection of its expansion phase, would start contracting with galaxy clusters converging, leading to a temperature rise in the cosmic microwave background, CHEM, owing to the blue shift of keen B photons. As the universe shrinks, stars would come so close that collisions among them become inevitable. In this model, roughly 500,000 years prior to the Big Crunch, M-type stars would heat up beyond their capacity to radiate heat away, thus causing them to self-destruct. This process would carry on with progressively hotter stars until O-type stars vaporize approximately 100,000 years before the event. In the final moments preceding the Big Crunch, the universe would become so intensely heated that atomic entities would disintegrate and be absorbed into the rapidly forming black holes. At the point of the Big Crunch, the universe's matter would ultimately be condensed into an incredibly hot and dense singularity, echoing the conditions of the Big Bang. This signifies the potential for the Big Crunch to be followed by another Big Bang, thus birthing a new universe.